So hi everyone, thanks a lot for coming. Today we have Yang Luo, who is associate professor at the University of Yunnan in China, and the floor is yours to give your seminar.
Okay. Hello, everyone, and thanks for the invitation. So here I would like to show our recent work on the MHD modeling of the accretion disk in the dual collapse models. So I would like to start with the point of the high redshift quasar observations. So in the left finger, you see this is a sort of summary of all the quasars from the survey until 2022. And you can see the distribution of the quasars in the luminosity versus redshift. Most of the high redshift quasars have been discovered using the color selection method, especially using the optical and near-infrared photometry survey data. So far, there are a number of almost 300 quasars observed at redshift higher than 6. Here, redshift 6 is approximately 1 billion years after the Big Bang, and is more or less the time of realization finally started. There are also a few observations that quasars already formed at redshift higher than 7 or even to 10. That means there must be a lot of supermassive black holes formed at such high redshift. In the right finger, the population, we show the population seen in these days is a JWST observation of the so-called little red dot. These objects are red in color, and many of them show broad emission line. There are a few broad emission lines have been detected, like the H-alpha magnesium-2 carbon-2 lines. The broad component has line widths ranging from 1,000 to 1,000 kilometers per second. These broad components are believed to be powered by the accretion onto supermassive black holes. In their sample, there are also a few observations shows outflow, and also this is signature of the early AGN feedback. And from the observation of the quasars, we can measure the mass of the black hole. And here, the top left finger, we show the summary of the mass of the black hole. And the mass of the black hole could be measured from the scaling relation from the line width and luminosity, especially from the magnesium-2 lines. In the left finger, we see the black hole mass ranging from 10 to 7 to 10 to 10 solar mass. Surely there are some uncertainty in the mass determinations, but these targets are quite red in color, so the mass here may be only a lower limit. I would like to highlight a few objects. So here the left one, the J0100, this target, it is observed at redshift of 3.3, and we found that it's showing the flux is boosted by the gravitational lensing. The mass of the black hole is so far the most massive, reaching to 10 to 10 solar mass. And another interesting two objects are the GNZ11 and UHZ1. These two targets are observed at redshift larger than 10, and they have mass is already 10 to 6 or 10 to 7 solar mass. And here, for redshift 10, it is corresponding to a Hubble time about 0.5 billion years. From the estimate of the accretion rate, say the right finger, it is found that this target more or less accurate at the adding ratio of 0.1 to 1. So most of the targets are in fast accreting stage. So here is the question: how this supermassive black hole formed? Why they are so massive at such early epoch of the universe? This is a big puzzle. So we can make some theoretical calculations. Suppose the black holes grows at a rate of the Eddington, one can estimate the growth timescale. Here from this equation, the mass growth is exponentially with time. Its motion is exponentially grows with time. Now, if we would like to form a supermassive black hole with mass of 10 to 9 solar mass, theoretical calculation shows that it requires almost 0.8 billion years, which is almost the Hubble time as the redshift of 7. So to form these observed supermassive black holes, we need to shorten their growth timescale. One can increase the initial black hole seed mass or increase the growth rate above the Eddington. So there are a few pathways to form the supermassive black hole seed. At first, there since for the seeds, they are initially not so massive, and then after they form, they start to grow. While a small black hole can form just after the Big Bang, the first possibility is that a stellar mass black hole seed could form the remnant of population star and redshift around 30 to 20. Then the stellar mass black holes grows at a super Eddington rate. The second possibility is the seed from the runaway collapses of a compact stellar clusters. The star clusters with about 1 million stars that merges and collapses and finally form a black hole seed with mass around 10 to 5 solar mass. And the third one, and the most appealing one, however, is the third alternative, which involve a direct bionic collapses to form a massive black hole seed of 10 to 4 to 10 to 6 solar mass. And in this talk, I would like to highlight this pathway. We believe this could be the most probable way to form the black hole seed. In the left figure, we show if the seed formation pathways could explain the observed supermassive black hole masses. For some example black holes at redshift of 7, given the black hole mass, and we can extrapolate their growth paths into higher redshift, where they start their initial seed formation. For this object with billion solar masses, even their seed start from redshift 30, the seed mass is going to be beyond what you can normally do with stellar evolution process. The seed mass have to be massive than 1,000 or even 10 to 4 solar mass. So that is to say for if the black hole want to grow to supermassive, a stellar mass black hole is not so possible. And also there are some numerical simulations. They want to check if the stellar mass black hole could grow super quickly and form the supermassive black hole. And the left finger, they found the growth parts of this black hole. They found that initially the stellar mass black hole could grow to 10 to 5, but after that, the growth is already stopped. The problem is there is low continuous mass fading. After that, then there is low continuous mass fading, then the black hole will not grow. The problem is also found in the star cluster pathways. Black hole could grow in the star cluster, but later, after it activates all the mass within cluster, then it never grows. There is low enough mass fitting them. So the first and second pathway to supermassive black hole is unlimited by the mass fitting. But here, we would like to show that direct collapse model have no such problem. And the largest advantage of the model, the direct collapse model, is the continued gas supply from the dark matter halo. The direct collapse model happens within an atomic cooling dark matter halo. Outside the halo, the large-scale filament could provide a continuum mass fading. Within the dark matter halo, the gas collapses to the center to form a black hole seed. So to best utilize the halo mass fading, we would let all the halo mass fading directly to form and grow the central black hole seed. So that means the star formation in the halo should be suppressed. That is to say, the gas within the halo cools down without molecular cloud or metals. If their star formation happens, the total halo mass fading rate could be shared into the star formation. Then the black hole growth rate would be decreased. But how to suppress the star formation? One can assume there exists a background star formation galaxy that release UV photons to destroy the hydrogen molecule. Surely the chance of a nearby star formation galaxy is smaller, but that also explains why the number of luminous quasars at redshift 7 is not so high. For an atomic cooling halo, we require the halo vapor temperature to be above the atomic cooling floor, above 4 Kelvin. So we need the direct collapse happens within a halo with a vapor mass of 10 to 8 solar mass. And also the vapor radius is also around a kiloparsec. The accretion rate toward the black hole seed could reach to 0.5 solar mass per year. So how the gas collapse within the dark matter halo? So the left finger, we show the temperature as function of radius. At the vapor radius, the kiloparsec scale, you see the temperature is short-heated into the vapor temperature around 10 Kelvin. Then within the vapor radius, the gas follows as a thermal collapse. The temperature is almost constant, and the density follows as a thermal collapse with R2-2 density profile. And the gas here is optically thin, and hydrogen recombination and traditional cooling are the most dominant coolant. We found that the gas could follow as a thermal collapse directly into the AU scale. But inside the AU scale, so when the gas reached to the NU scale, the density could be as large as 10 to minus 10 gram per cc. The gas here now become optically thick. Afterwards, the radiation could not escape. As the radiation trapped within the inner region, the collapse process will not be the isothermal collapse, but will turn to more or less the adiabatic collapse. In our early work, we had run a radiative transfer model. We had found that after the gas become opaque, the radiation would halt the accretion and there form a core. Around the core, you can see a disk forming here. Here, say the left finger for the density slice at 2 times 10 to minus 3 parsec. A core formed at the center, and surrounded the core is an accretion disk, and works like a filament accretion. But later, the filament will form a disk. From the right finger at 2 times 10 to minus 5 parsec, the core is more or less spherical. But look at the density slice, the core is surrounded by a hot envelope. In some theoretic models, the core is also called a supermassive star. But here, the core is not so similar to what we learned about a supermassive star. This core is growing with a fast accretion rate around 0.1 to 1 solar mass per year. And the core is surrounded with a hot envelope. This is not described in the early supermassive star modeling. And we run it longer for the supermassive star evolution, since the accretion rate toward the central core is quite high, and we found some feedback from the core accretion. Here we can see that the outflow are generated above the core. The outflow collide with the inflow and form a shear. The core radiates at the Eddington luminosity, and the luminosity is mostly from the accretion process. we have measured the temperature and the density of this core. See the middle finger. We found that the temperature is related to the density with the power law index on 0.2. Here, the power law index 0.2 corresponding to a polytope index n equals 5. This is not a typical supermassive star in the old literatures. Some early theoretical model of supermassive star imply the supermassive star is an n equals 3 polytope, and with radiation force dominate the stellar structure. But in our work, we found it is more likely an n equals 5 polytope. Now, after the optical seed core is formed, the core could collapse into black hole seed at a later time. So the question is that could the accretion disk around the core still provide a continuous mass fitting, such that the core could grow to be supermassive? There are some early papers that shows the accretion disk around the core could fragment, then the core growth could be limited. In order to answer this question, we run a numerical simulation with MHD. We run a cosmological zoom-in simulation. At first, we select a proper dark matter halo with a zero temperature above the cooling floor, and we run the MHD modeling for this selected halo and run it until the gas in the halo collapses to form a supermassive star and also the surrounding accretion disk. We use the Enzo code. Enzo code is an adaptive mesh refinement code. They use the AMR technique. The gas is modeled with magnetic hydrodynamics, and we use the hyperbolic cleaning technique to remove the magnetic divergence. The domain box is set at 1 megaparsec per moving, and the zoom-in region is a few kiloparsec per moving. It is a few times that we had a zero radius. We set the resolution at 10 to minus 5 parsec. So now we got the result. In our MHD modeling, the collapse happens at around redshift of 11, and the collapses happens very fast. Only after 1/4 time, a core is already formed in the dilated center. Around the central core, a disk is surrounded with a size of 10 to minus 2 to 0.1 parsec. The disk connected with the outer region with spiral arm extended to 0.1 parsec. We have measured the mass of the core and the disk. The total mass within 0.1 parsec exceeds 10 to 4 solar mass. More than 19% of this mass belongs to the accretion disk. Here, the dark matter fraction is not important, so we can conclude the disk is self-gravitating. But limited by the computation, we have involved the disk about 2.5 kiloyear after its formation. But the most important result here is that the disk is stable against fragmentation. So we don't find any fragmentation here. We have run a comparison model without MHD. This is the left top panel. Without MHD, the disk do fragment, and we see some fragment inside here. But with MHD, we find no fragment. The disk is stabilized by the magnetic field. In our current model, we didn't introduce radiative transfer, just MHD. But in our early work with radiative transfer, we found a similar result. See the right finger. With radiative transfer, we see the disk also shows the fragment. The disk is stabilized by the radiation pressure. So combined with our models, we can clearly see that both magnetic field and radiation pressure could stabilize the disk. Without fragmentation in the disk, that means the disk could continuously provide mass feeding to the central growth. So black hole seed could grow fast to be supermassive. So far, the whole picture of the dual collapse model is quite beautiful. So the model we believe is the most possible way to form the supermassive black hole. There are some observations of the high rate shift quasars. They found that some emission lines from the matter, like the magnesium 2 carbon 2 lines. For example, here, as they have one paper, they found the ratio of the iron over magnesium, the metal abundance is more or less constant with redshift. Here you can see the abundance ratio at redshift 7 is almost consistent with the lower redshift AGNs. So there are some papers suggest this constant ratios could be a result of star formation or fragmentation in the accretion disk. But in our dual collapse model, we find no star formation in the disk. So how to explain the matter lines? There is one paper in 2018. They found the H3 from the black hole seed could analyze the medium at a few parsecs scale, and then enhance the H2 formation here. So with H2 formation, there could be star formation. In this paper, in this 2018 paper, they indeed found the H2 formation is enhanced by the H3 in the direct center at around, say the bottom finger at 5 to 10 parsec. The H2 fraction is indeed increased. So we think this could be the reason for the high rate metal productions in the AGN. But surely the star formation happens at around 10 parsec, but not in the scale of the accretion disk. So now let's turn to the structure of the accretion disk. Here we show the disk structure in view of the face on and edge on. The top panel shows the face on, and the bottom panel shows the edge on. In the bottom panels, the black solid line marks the edge of the disk, and we show the fingers in within the 2 times 10 to minus 2 parsec, and the vectors in the left panel show the velocities. We can clearly see the outflow generated above the disk, especially in the polar region. In the middle panels, we show the slice of the magnetic field. The magnetic field is mostly confined within the disk. In the outflow polar regions, the magnetic field directions follow the gas motion. The right panel shows the ratio of the magnetic pressure over turbulent pressure. Within the disk, the ratio is almost close to 1, but outside this, the magnetic field is not important. In the outflow region, the outflow is mostly dominated by the magnetic field, and we can see the ratio could reach to 10. And we have measured the disk thickness. The disk thickness is almost constant with radius, and the disk is quite geometrically thin. We got the thickness aspect ratio H over R, which is around 0.1 to 1. So it's geometrically thick. Here we show the H over R ratio as function of radius in the right finger, and shown as the red solid line. We have checked the thermal and magnetic field and what's the turbulent pressure contribution to the disk vertical supporting. We can find that the core within the 3 times 10 to minus 4 parsec, it is thermally supported. But in the disk, within 3 times 10 to minus 4 parsec to 5 times 10 to minus 3 parsec, the disk is magnetically supported. Here you can see the green dotted line. But at the outer part of the disk, for radius larger than, say, 3 times 10 to minus 3 parsec, the disk thickness becomes thin. And we found it is the accretion flow to compress the disk. And then within the disk, we check the magnetic field evolution in the disk. The initial magnetic field in our model is set at 10 to minus 15 Gaussian. Then after highly visualized, the magnetic field quickly increased the magnitude. So shown in the left figure, from the kiloparsec to parsec scale, the magnetic field is amplified efficiently. The mechanism, and we found the mechanism for the field amplification is mostly from the gas compression. The shocks and the developed turbulence in the spherical cliffs are responsible for this amplification. But at sub-parsec scale, we're still smaller than 0.1, for example, at 1.1 parsec. At the end of the simulations, we can find a break in the magnitude of the field. Here is the brown solid line, and you see at 0.1 parsec, there is the break in the field magnitude. This break is caused by the saturation of the field in the accretion disk. In the right figure, we show the field growth within the disk. We show the magnetic field magnitude as a function of time. And you can see at each disk radius, the field initially grows very quickly, but then reach to a maximum limit. At this maximum limit, the magnetic field energy is almost comparable to the gas thermal energy. That it means the magnetic field has reached to the equipartition state. The dashed line are shown for the poloidal field, BP component, and the solid line for the toroidal field, B5 component. The BP component grows faster than the B5 component, but later after, for example, 1.5 kiloyear, after the disk reach to the equipartition, the B5 component is amplified by the disk rotation and then dominates the BP component. We have also checked for the maximum value of the black hole, the maximum value of the field, field magnitude, and indeed it is consistent with the maximum saturated value predicted by the MRI. So we believe the field amplification in the disk is caused by the MRI. And also to test if the MRI do operate here, so we made the magnetic energy spectrum. We made the magnetic energy spectrum as function of the spatial layer. In the x-axis, the unit is per parsec. So move to the right, it is the smaller inner radius. On larger scale, for the values of k smaller than 1,000, the spectrum is proportional to k to 1.5. This is a manifest of the operation of smaller scale turbulent dynamo, or the MRI. The field is amplified by the dynamo associated with the MRI, and the MRI each side the turbulence. While on smaller scales, and here for k larger than 1,000, and this is the scale within the disk region, the energy spectrum shows a break, and it becomes proportional to k2 minus 1.5. The appearance of the k2 minus 0.5 power law, it reflects the shorting of the small scale dynamo. Later, we'll show that this shorting of the smaller dynamo is also manifest as the magnetic buoyancy above the disk. As the magnetic field is amplified the MRI, so we measure the disk alpha coefficient. The alpha is the ratio of the torque over the gas pressure, so we can define the effective alpha here, shown as the equation. We can show in the figure, we see that the alpha is almost comparable to 1. In the early black hole accretion disk simulations, the alpha is around 0.1, But here, all alpha is larger than 0.1. So why it is so? We believe it could be the result of the self-gravity in the disk. Showing earlier, we see the spiral structure at 1.1 parsec scale. We found that the spiral structure is a manifest of the gravitational torque induced by the spiral structure. And this spiral structure could trigger a global instability. And this instability could provide a very efficient way of angular momentum transfer. In case of this global instability, alpha could exceed 1. So we think in our self-gravitating disk, both MRI and the global spiral structure are responsible for the angular momentum transport. In our work, we found the magnetic field in the disk is amplified by MRI, and the field saturates after the disk switches to equipartition. However, we find one recent paper by Hopkins group. They have modeled the black hole disk formation. In their result, shown as the left finger, outside their black hole disk, around 0.1 to 1 parsec, the field is amplified by the compression that is similar to our result. But the difference comes from within the disk. Within the disk, we got a totally different result. They never found a saturation of the magnetic field. There is no break in the profile. Here in the right panel, they show the field magnitude compared to the theoretical saturated magnitude by MRI. Their magnetic ratio is almost everywhere is a lot higher than 1. So they conclude the field is amplified by the flux freezing, not by MRI. The flux freezing means the poloid magnetic field could be dragged inward by the inflow and dragged into the disk center. Because the magnetic field is conserved and the flux is proportional to the B times R22. So with smaller radius, the magnetic field could increase accordingly. But why the magnetic field in their paper does not saturate? Why there is no buoyancy or buckling in their field? We don't know. We have no answers. Maybe this is related to the ability of the accretion flow to drag the poloid field inward. So we have also calculated the magnetic field profile in the vertical direction of the disk. The beta, we calculate the beta as function of the vertical height. The beta is determined as the ratio of gas thermal pressure over the magnetic pressure. With smaller beta value, the disk magnetic field becomes stronger. For the top panels, we present the vertical structure of beta value. The x-axis is the vertical height, and z equals 0 means the disk midplane. This profile are shown at radius of 2 times 10 to minus 3 parsec. The disk thickness around 10 to minus 3 parsec, so h over r here equals 0.5. Here, the different colored line presents the profiles at different time, and at the early time of the disk evolution, the disk surface have a smaller beta. Here you see the dip in the profile, close at z equal 0.10 to minus 3 parsec. So that means it is the disk surface that is largely magnetized, but at later time, the brown line, the disk middle plane get magnetized. The bottom panel shows the beta value as function of radius. Within the core, for r smaller than 2 times 10 to minus 4 parsec, the magnetic field is not important. Beta is almost close to 1,000. But within the disk, around 2 times 10 to minus 4 to 10 to minus 2 parsec, the disk has a beta almost smaller than 1, with beta around 0.1 to 1. And in the right panel, the right bottom panel, we show the ratio of B5 over BP. Initially, the disk is dominated by the BP component, while at later time, because of the disk rotation, the toroidal B5 component grows with time. Here you can see the ratio in the disk is almost higher than 1. In our work, the magnetic field growth is limited by the saturation. After the saturation, we found the magnetic field could be expelled from the disk surface, which is the manifest of the Berkeley instability. Here you can see the slides for the magnitude of the magnetic field, and the vectors show the direction of the magnetic field. At the early time, the left panel looked at the bending of the field. This is a simulation of the magnetic field Berkeley. The right panel taken at the end of simulation, it shows a Berkeley field is being expelled from the disk. Along with the Berkeley, the gas also flows above the disk and forms the outflow. We have checked that the outflow is strongly magnetized with beta almost reached to 10 to minus 5. The outflow is driven by the magnetic pressure gradient. We believe it is the Berkeley process to limit the magnetic field amplification. And for our geometric thick and magnetized accretion disk, we found one interesting feature here, the backflow in the disk middle plane. In this figure, we show the half size of the disk. In the left panel, we show the total stress. From the Maxwell and turbulence stress, the vectors mark the magnetic field. But in the right panel, the colors mark the radial velocity. The radial part, the radial color presents the positive velocity. That means that implies an outward or outflowing direction. The blue region is the inflow. In the dispolar region, we say the outflow is seen, but the interesting part is the backflow or the outflow at the disk middle plane. That's interesting. So why the outflow or the backflow at the disk middle plane? When we got this result, so we want to explain the backflow. So we searched some literatures, and we found that this backflow in the middle plane is already found in the last centuries. Here in the right finger, you see even in the 1984, they already found the gas flow. The gas is flowing outward in the middle plane. The inflow only happens at the disk surface. They attribute to this backflow as a result of disk convection instability. For certain conditions, the accretion flow could become convectively unstable, and this instability produces vortices. Here you can see the convecting bubble. And along this bubble, it shows the backflow in the middle plane. And later, at 2000 years, the theoretical work, it shows that the backflow depends on the value of the alpha. For disks with smaller alpha, the convective bubble could be generated. But all of this work is based on the hydrodynamic without MHD. And later, they also have simulations with MHD. And also, they also found the similar features, the backflow in the middle disk. And in this 2018 paper, they also found the backflow in the disk. But their explanation to this backflow is caused by the relative gradient of the stress in the vertical direction. So here in the left finger, you see the central middle plane, and the stress is relative as function of z. And they believe is this relative gradient can cause the angular momentum be transferred from the disk surface to the middle plane. and therefore a convective bubble could be formed, and also the bed flow. We also measured the total maximum stress in the vertical direction. So for the theta phi component here in the right finger, the blue line, we do find a negative gradient of stress within the disk. Here inside the disk for Z over R around minus 0.5 to 0.5. And the gradient is negative. So this is consistent with the 2018 paper. Recent years, there are more investigation of the backflow in this 2022-23 paper. This suggests it is the Prandtl number responsible for the backflow, not only depends on alpha, but more depends on the Prandtl number. The Prandtl number is the ratio of the viscosity over resistivity. In their simulation, they found for smaller Prandtl number, the backflow is more significant. But with increasing of the Prandtl number, for example, when the Prandtl number equal 0.6, the lower limit, the lower bottom panel here, you see there is low backflow. So the belief is the Prandtl number is the most important to control the existence of backflow. Okay, that's all for our disk, the accretion disk. But here I will not show in our radiative transfer model or in our MHD model, we do find the outflows above the disk. But here I will not highlight the importance of this outflow. So usually we want to observe the central object, the central supermassive star or the central accretion disk. We can measure and if we can measure the Lyman-alpha radiation. But for Lyman-alpha radiation, there is some problem. Thus, for Lyman-alpha, we know it is a transition from 2p to 1s state. But at higher density, there are collisions that could make the protons at 2p state being converted into 2s state. That means at higher density, there will be low Lyman-alpha, but only the 2s to 1s, the 2s to 1s transition was the two-photon emission. That is we call the Lyman-alpha distortions. So the left finger, you see with the density increase, the escape fraction, the blue or the green line, with the density is higher, the escape fraction quickly decrease. But vision is the outflow is very important. The outflow can clean the gas above the disk. Therefore, you can reduce the Lyman-alpha optical depth. So the Lyman-alpha could be escaped along the outflow region. And the lower panel, we have made some monocolor simulation. We checked for that the finger, the right bottom panel, the x-axis is the tolerant density, and right panel, the right axis is the Lyman-alpha flux. So for higher tolerant density, or we say the outflow is stronger, is weaker, or with their low outflow, the tolerant density is very high. So you see the flux is very smaller. But if you turn to left, will move to the left. When the tolerant density becomes smaller, that means when the outflow is stronger after the outflow clean the gas, the flux, the Lyman-alpha flux increase. That means the Lyman-alpha could escape along the outflow region. And we believe in the near future, the GWST could detect some Lyman-alpha signatures. Okay, now I want to come to the conclusions. We believe the directionalized model is the most feasible way to form the supermassive black hole at high redshift. And the largest advantage of this model is the continuous mass fading to the seed growth. And we have run image modeling of the accretion disk. We found the disk is self-gravitating, geometrically thick, and also is most important is gravitational stable. The disk rotation along with the MRI could quickly amplify the magnetic field until the magnetic field gets saturated. And this field saturation is related to the magnetic field buckling. And we found one interesting feature in the disk is the backflow at the disk midplane, which will also be a signature of convection instability. And also the last point, the last point is that if the direct collapse accretion disk could be detected in the near future, we think it is possible, but this will be put in the near future investigations. Okay, that's all for this talk, and thank you for your listening.